The conference today will be given by my colleague and good friends of the BTL, Professor Jose Luis Sanchez. The title of the presentation is Advanced Biofuel. I met Professor Sanchez a while ago. I think it's been more than 10 years now, Jose Luis?
Yeah.
Something in that range. So Professor Sanchez obtained his degree in chemistry in 1992 and his PhD in 1999 at the University of Zaragoza. Since 2003, he is associate professor at the Chemical and Environmental Department of the same university. And in 2017, he was invited professor at the University of Sherbrooke. I remember this part, hopefully. His research is framed in the Thermochemical Process Research Group. The main research line are thermochemical processing. So Jose Luis worked quite a lot on pyrolysis and gasification of biomass and residue. He worked a lot on black liquor. He loves lignin and work on different like nasty stuff such as meat, bone meal, and sewage sludge. And of course, biodiesel production. So I guess there will be a link to be made with our colleague Eduardo on this part. The research experience is focused not only on basic research, but also on industry-oriented research in order to boost the transfer of technology. So what they're doing pretty much as what we are doing here in Sherbrooke, although they have bigger infrastructure, bigger equipment. Professor Sanchez has participated in 13 public-funded projects and 7 research contracts with private company. He has published 43 papers in peer-reviewed journal, has attended to more than 40 international conferences, and has developed 1 patent. His industrial research has focused on the development of the gasification process, where he has participated in the design, the startup, and operation of a pilot. So about 100 kilogram per hour of biomass feed in a fluidized bed gasification plant for sewage sludge, and a commercial unit of about 650 kilogram per hour downdraft biomass gasification plant facilities. Finally, in 2001, he received the 3M Foundation Award for Technological Innovation for the work carried out in sewage sludge gasification. So Jose Luis, we're pretty happy to have you here again with us, not physically, but in spirit. So without further ado, the floor is yours.
Okay, thank you very much, Jean-Michel. Thank you very much for having me and for this invitation. I have prepared a short, well, maybe not so short for you, talk on advanced biofuels. Before starting, I would like to do several disclaimers. First of all, this is a COVID-free talk. I think that even it seems that the world is ending right now. In the short term, it's affecting us, but it won't affect us too much in the medium to long term. I think that we either learn how to live with the virus, or we learn how to die with it, but it won't make a difference in the way that we behave and the things that we do. At least not a too big difference. The second one, I would like to cool down your expectation. This is not an advanced talk on biofuels. It could be like a small talk on advanced biofuels, which is different. And well, I feel myself amongst friends, so please feel free to interrupt me at any moment and ask or comment about anything, which probably will be this way less boring than letting me talk all the way. Okay, this is the outline that I'm going to follow. Most of it, if not all, you already know, you already have heard, but I just thought it was interesting to put all those things together. First, I will comment a bit on the energy consumption that we are doing as a race in this world, and I will focus a bit also on the use of oil. Then I will comment the environmental consequences that this use of fossil fuels is having, and we are already witnessing it. As a solution for stopping this or mitigating these consequences, I will speak about biofuels, about the classifications that we can find, and a concept that is being used by different governments, which is the concept of advanced biofuels. I will also speak a bit about the policy that the European Union plans for the next year. The most technical part, which also is not really very technical, I will speak a bit about the different process to introduce advanced biofuels on the three probably most significant or important fossil fuels that we are using right now, which are gasoline, diesel, and jet fuel or aviation kerosene. And we'll conclude with very short messages. So here you can see in this figure the evolution of energy consumption from different sources of energy that we are using. The most important is oil. The next one by amount is coal and natural gas. The three of them make about 85% of the energy that we are consuming at this moment. Here you can see that the share of oil, for example, is decreasing, but it is mainly due to the increase of natural gas that we are using in the world. Also a little bit the small increase, small in amount increase of renewable energy, which only accounts for about 11% of the energy primary energy that we are consuming. Focusing on oil, you can see that the oil consumption in this figure is not evenly distributed. Here in this area, you can see that the color is darker than the color that we have here, meaning that you consume more oil per capita than the rest of us. There is one figure that I've been always curious about, and that there's not usually appears on the news. Also, it's very important, which is when will oil be depleted? When will oil run out? Because we are not producing oil, we're just consuming. So with a very simple math, you divide the amount of proven reserves of oil that we already have discovered, and if we divide it by the oil consumption, oil production rate that we have in the last year, we get this number, which is saying us that in 50 years we will run out of oil, which is the main energy source that we are consuming at this moment. I don't know what to think about 50 years. To me, it's fair enough, because more likely than not, in 50 years, I will be pushing up the daisies. But those of you in the audience which are younger should be at least a bit concerned about this. The products that we use of oil are this one that you have here in this slide. I have highlighted gasoline, diesel, and kerosene. That represent more than half, 60% of the oil that we are consuming, and we are using them mainly for transport. Also, there are fuel oil that is also used in marine transport, and part of the gasoline is used for other purposes, or diesel. Mainly 61% of the oil we use we are using this for transport. Obviously, it's not new. It's not in the news for you that this use of fossil fuels has strong environmental and negative environmental consequences. We are emitting a lot of CO2. Of all the CO2 that we emit currently in 2019, about 15% comes from transportation. In more important, the use of electricity and heat as a single source. Not only CO2, but also methane is an important gas for the global warming. But these numbers are referred to average CO2. In 2015, the Paris Agreement set the limit to try to limit the global warming to 2 degrees Celsius over the temperature that we have in pre-industrial times, before we started using the fossil fuels. Now we already have increased 1 degree, so we have like one more to play with. But the Intergovernmental Panel of Climate Change published a couple of years ago that the consequences of going to 2 degrees compared with the consequences to allowing the temperature to increase only by 1.5 degrees are worse, much worse, in what concerns the sea level increase that will affect more people, the loss of biodiversity, and the probability of melting the ice on the polar casket that probably will be irreversible. In order to have an increase of 2 degrees C, we will need to go to zero emissions by 2075, and to not allow more than 1.5 degrees, we will need to go to zero emissions by 2050, in 30 years from now. This is the trajectory that we are following, meaning that around we do nothing, around in 20 years we have reached the 1.5 degrees, and temperature will still be increasing. If we stop right now emitting CO2, temperature will still increase because of the effect of the CO2 that we have already emitted. Here you can see that in order to be sure that we are around 1.5 degrees in the average temperature over the pre-level temperature, by the end of the century, we will need to decrease, in 20 years, we will need to decrease to zero the CO2 emissions, and also not only CO2, but other gases as methane or nitrous oxide. So the situation is not really hopeful. There's like bad consequences in the near future. But in order to stop this trend, we need to use fuels from biomass. And the fuels from biomass you can classify in different ways. The most simple, and one I don't really like too much, is the adopted by the United Nations. The United Nations distinguish between biomass, which is the raw material. You can see here the different materials considered that can suffer a preparation process and be converted in biofuel. And the United Nations considers solid fuel, gaseous fuel, and liquid fuel. When we use the biofuel by a conversion method, we obtain energy, would be bioenergy, which in the end is only power and heat. This classification is pretty simple, and I don't think it reflects the complex scenario that we have speaking about biofuels. We are more used to hear about the biofuels for its generation. So first generation biofuels are produced from edible materials as sugar, starch, or oil, and through a simple process we can obtain a biofuel as ethanol or biodiesel. Obviously, this was the cause of the food versus fuel controversy. So we move into something that does not affect the price of food as second generation biofuels. So we start from something that is not edible as lignocellulosic biomass, and through a process that needs to be more complex because the raw material is more complex, we produce ethanol or methanol or biodiesel or other compounds that can be used as fuel. For example, the cellulosic ethanol that you all know very well, better than me, of course, can be converted into ethanol, or a residue as used cooking oil can be converted into biodiesel. One step more are third generation biofuels. In this case, biomass, considered biomass, is a low efficiency way to convert solar energy into energy. So we have turned into algae that you also know very well, that are more efficient and can be produced on non-arable land, just avoiding the use of change, the land use change. Thus, if we produce algae, we can produce lipids and go to biodiesel, or produce hydrocarbons and go to ethanol or other fuels. There's one step more, which is the so-called fourth generation biofuels. They are also produced on non-arable land, but the driving idea of fourth generation is to improve the proton to fuel efficiency, which is very low for biomass, is better for algae. But if by genetic engineering and synthetic biology, those microorganisms as yeast or bacteria or algae can be transformed into more efficient sources of biomass, we can produce in the future more energy, or using these microorganisms in a special system, which are under development as fuel cells, which use microorganisms in the cathode or in the anode to produce products as biofuels or other products. So that's another classification. More recently, governments have started to speak about advanced biofuels, and the definition of advanced biofuel depends on where do you look for. For example, your neighbors down in the south are pretty simple in the definition. For the U.S. government, advanced biofuel is a renewable fuel that is not produced from cornstarch. So if you take, like, I don't know, rice or sugar and produce ethanol, it's considered an advanced biofuel. Anything but cornstarch. We in Europe are a little bit more sophisticated, and according to this RED II directive, or Renewable Energy Directive, considers different concepts. If from biomass we produce something that is gas or solid and we use it for fuel, this is called biomass fuel. If we produce a liquid from biomass and we use it for energy, but different from transport, I mean heating or cooling or producing electricity, it is called bioliquid. If the liquid is used for transport, then it's called biofuel. And if the biofuel is produced from a feedstock that is in a list, then it is called advanced biofuel. This is the list. Sorry for the slide, because it's full of words. Basically, the feedstocks to produce advanced biofuel are algae and residues. Not all the residues. Some residues are excluded in another part of the directive. Now I will show you now. Straw, bio-industrial residue from biomass, husk, corn cobs, or anything, sewage sludge, glycerin is considered a proper feedstock for advanced biofuel. I have marked here in red this residue because I was not aware that in Europe palm residues were important. I will maybe later explain why it's included. The residues excluded from the advanced biofuel definition are used cooking oil and animal fats. I think this is because European Union wants to avoid not only the so-called indirect land use change, but also the direct land use change and the use change of the different residues. These residues can be used for, I don't know, animal food or for other purposes, and the European Union wants to limit the amount of the residues that go to biofuels. So in short, here an advanced biofuel is a liquid fuel that is going to be used for transport and is produced from certain residues or algae not from animal fat or used cooking oil, and they must meet certain sustainability criteria to avoid the impact that the use of fuels has on soil quality, biodiversity, and last use change. There is one concept that I think is not explicit in this definition, which is the drop-in concept. Actually, what the industry wants is a biofuel that can be used directly in the system that we have, in the infrastructure that we have. The storing, the delivering, the pipelines, the engine or the turbine must not suffer any change as a consequence of introducing the advanced biofuel or the biofuel in the system. Some people consider that it's also needed a low sodium content to be considered a drop-in fuel, which is I don't think totally true in what concerns, for example, ethanol for gasoline. So why are advanced biofuels important? Advanced biofuels are considered as a part of the renewable fuels that will count more on the CO2 reduction. So that's why they are defined this way. What are we trying to do in Europe, or what is the European Union trying to regulate or legislate about biofuels? Well, in 2018, this directive was enacted, substituting an older one. And the goal of this directive is to increase the use of renewable energy at least at 32% of the primary energy in about 10 years. For this, considers the distribution in electricity, heating, cooling, and transport. In transport, in 10 years, in Europe, we should be using at least 14% of renewable energy in the transport sector. Taking into account the situation and that well, 1 year ago, approximately, we were about 1.9% of renewable energy in transport, and that we use a lot of oil, which is basically the source of energy we use for transport. Maybe you can consider that this is too ambitious to get this in 30 years. I could think that too, but 1 year later of publishing the directive, at the end of 2019, the European Union published the so-called European Green Deal. The European Green Deal is the steps that the European Union wants for all the partners, for the country members of the Union, to be climatically neutral by 2050. That means that by 2050, we should be emitting zero CO2 in all the sectors: transport, food, heating, electricity. And to do that, they want that the economy, or the European Union wants that the economy is not to be affected. And now countries that maybe have less resources are left behind. In the presentation, the EU President, Ursula von der Leyen, that you see there, did the analogy that this was Europe's man of the moon moment, because it's really a strong purpose to be zero neutral. Not really sure what was she referring to. Maybe we'll see in a few years. Here you can see the timeline that we are going to follow by 2030, in 10 years, 9 years. Europe should be emitting half of the CO2 of greenhouse gases that were emitted in 1990, and get to the net zero emissions by 2050. For that, several action lines are proposed in agriculture, in food. I picked two, which is clean energy, which involves the decarbonization of the energy sector, and sustainable mobility, which involves the use of, well, probably electric cars and the use of alternative transport fuel, renewable fuels. There are several processes to do this, and several things that we can do. I will comment shortly on several processes for gasoline, for diesel, and aviation kerosene, which are some of them are the same, because gasoline and diesel and aviation kerosene have more or less the same chemical composition with different carbon length. Regarding the gasoline, it's mainly used for road transport and for like private transport. I don't know exactly what the future is. As you know, doing prediction of the future is complicated, but you can see here that the market thinks that we all be soon the proud owners of a Tesla car. Actually, Tesla is at this moment the car company with more capitalization, has more value on the market, even though the number of cars that the Tesla produces in 1 year has nothing to do with the cars that a big producer as Toyota, which was the #1 till Tesla erupted in this way of market value. But the future of cars is probably electric. Even though I don't think that we all have soon a Tesla, and we all can use only electric cars for transport. Here, for example, in Europe, in the cities, cars usually go a very short trips, and they are stopped most of the time. So electricity can be reasonable. I don't know if in Canada with big spaces it's possible to have only electric cars. So till the time comes, we need to find a substitute for gasoline. Gasoline, you can see here, is a complex mixture of hydrocarbons, linear, branched, cycloalkanes, and aromatics, within a range of carbon from 4 to 12. The first thing that we are already doing is blending it with ethanol. Ethanol is an advanced biofuel if it's produced from residue, not from corn oil or from food. Probably all of you know that the fuel market is regulated. In order to commercialize a fuel, you need to fulfill the properties that a standard sets. In Europe, in order to be blended with gasoline, ethanol must meet a standard. This one, the EN 15376, that sets the composition in alcohol of the ethanol, the amount of other alcohols than ethanol that can have, the amount of water, and the other properties. At this moment in Europe, we are using E5, which is 5% by volume of gasoline. I think that soon it will change to E10, and by 2030 should be E20. I mean, 20% of the gasoline should be bioethanol, renewable ethanol. Cars are prepared. Probably you don't see here the picture, but in this car it indicates that it can use from E0, it means pure gasoline, to E25. This is not new. Brazil is the leader in this sector. It's been using ethanol and ethanol and gasoline mixture from a long time ago. In this case, won't be advanced because they use mainly sugarcane as the sort of ethanol. Well, that will go for the 20% of the gasoline. What happens with the 80% or 95% at this moment? Well, we can produce gasoline by a process that is already well known and commercial, which is the Fischer-Tropsch process. if we are speaking about biomass or advanced biofuel, we would need to do a gasification of the biomass, producing a syngas, which is a mixture of CO and hydrogen in a certain proportion, hopefully higher 1 to 2 hydrogen to CO to hydrogen ratio. And with the use of catalyst and pressure and temperature, we produce water to remove the oxygen, and usually linear alkane. The number of carbons that this alkane has depends on the catalyst and operation conditions. Some other byproducts or that you can have are olefins and alcohols. At the end, you produce a mixture of hydrocarbons. When you start from biomass, usually you have a hydrogen to CO ratio lower than 2. In this case, an iron-based catalyst is more suitable for the process, and using the high temperature Fischer-Tropsch process. When you start from, for example, a natural gas, and then you have a higher hydrogen to CO ratio, even higher than 2, you can use cobalt or iron as a catalyst and go to the low temperature process. The range of products that you produce depends on the conditions and the catalyst. Once you have the product of the Fischer-Tropsch reactions, you need to go to a refinery step, which is already commercial and very well known by oil industries or oil refineries. That would be a solution for the gasoline. Another solution, which is already commercial, is the methanol to gas process, which was developed by the oil company ExxonMobil to produce an advanced biofuel with this method. The same first step of gasification of biomass would be needed, using the syngas to produce methanol. Methanol, once you have it, doesn't matter where does it come from, you produce gasoline by dehydration in a two-step process with 2 different catalysts. In this process, you not only produce linear alkanes, but also a range of products which fall in the similar range of oil gasoline, fossil gasoline, producing aromatics and olefins and alkanes that can be either reformed or be used. That is 2 commercial processes that could be available right now if we can get a proper classification of biomass and a clean enough syngas to be used in the catalytic reactors. There are more that are under development. For example, this process is published in a scientific journal at the lab scale by aqueous phase reforming of cellulose, aqueous phase reforming which is a step of hydrolysis and hydrogenation. Polyalcohols can be produced as sorbitol that you have here, and in a second step, the hydration and hydrogenation of the polyol, the sorbitol, will produce linear alkanes. So there are like many processes that can be used. But what about diesel? For diesel, we have that is similar to gasoline, heavier hydrocarbons. The carbon number ranges from 12 to 20. We have paraffins, normal and branch. We have cycloparaffins, aromatics, and olefins. The standard that sets the quality of the diesel to be commercialized only sets 2 things about composition, maybe 3 if you take into account water. The polyaromatic hydrocarbon content that cannot be higher than 8% due to the soot production that comes from the combustion of these compounds and for health reasons, and biodiesel or fatty acid methyl ester that at this moment is used in a 7% volume in the diesel that we are consuming in our gas stations. the use of other hydrocarbons that come not from oil but from biomass is allowed, and in this case, if they are hydrocarbons and not fatty acid methyl esters, the standard says no limit on the amount that we can use. If we produce any compound that does not alter does not change the properties of the diesel, we can use anything made from biomass. Well, speaking about advanced biofuels, the transitification of lipids obtained from algae would be considered advanced biofuel. This process is very, very simple. You already know it. It can be carried out almost at home, atmospheric pressure, low temperature, using an excess of methanol to avoid the equilibrium that is present, using a cheap homogeneous catalyst as a base or other different catalysts. So in this sense, we can use biodiesel from algae as an advanced biofuel. There is no physical limit to the amount of biodiesel that can be used in an engine. The thing is, biodiesel, as being an organic material and it has oxygen, is more prone to oxidation and has worse cold flow properties. Thus, that the limit that is being used of 7%, not really sure if it will be increased or not. But you can use it in the engine, but you cannot store it for a long time. You cannot use it usually at low temperatures, which are also familiar for you, I think. The option that is already commercial is the production of directly a diesel fraction by hydrogenation of lipid of oil. The process is usually called HVO, for hydrogenated vegetable oil, but the oil, the lipid can be from fat or can be from algae. The name of the process is the same, although it's not vegetable, the raw material. In this process, you need to react the lipid, the triglyceride, with hydrogen at high temperature, high pressure, in the presence of catalysts, and with that you produce a range of products. Instead of producing glycerol, which happens in the transerification, you produce propane by the hydrocracking of the triglyceride. This carboxylic acid that forms after the cracking is, well, if it has double bonds, the double bonds are saturated, and then the oxygen is removed by dehydration, by decarbonylation or decarboxylation of CO2. There are also some lateral reactions of branching the linear fatty acids, the carboxylic fatty acids that we have. So at the end, you produce something which is pretty similar to the diesel, except maybe from aromatics and cycloalkanes. This process is commercial. The leader at this moment in this process is the Finnish oil company Neste. Neste has 4 production sites. Only one of them, the refinery of Singapore, is a true total biorefinery. They use only renewable. And here you can see, I don't know if you read it because it's small, the residues that uses according to the web page, the feedstock that Neste uses. Use cooking oil, animal fat, and palm oil residues. So I think this is the explanation of why we are not avoiding the use of this, which is not grown in Europe, but in Asia. The last fuel that I will want to talk to you about is aviation kerosene. It is not the more important, but aviation is the sector that most is increasing the CO2 emissions, because aviation in the last 1 or 2 decades has grown in importance for everything, for connectivity, for commerce, or everything. Biodiesel, jet fuel or aviation fuel is similar to gasoline and to diesel. It falls between the range of number of carbons. It goes between 8 and 16 carbons, and usually has a typical composition that you show here. Linear paraffins, about 20%, isoparaffins, branch paraffins, 40%, naphthenes or cycloalkanes, 20%, and aromatic content between 20 and around 20%. The standard that sets the properties that jet fuel must have in order to be used in a plane in a commercial way is this one that you have here, is the D1655, and apart from water, the only composition requirement that this standard has is the aromatics content. Aromatics content should be no lower than 8% and not higher than 25%. The high limit is due to the pollution that you produce when you burn aromatics. The soot production in the turbine, it's believed to be mainly caused by aromatics, so you don't need, or you don't want a high percentage, no higher than 25. And the 8% content is due to material compatibility. The turbine has seals and gaskets and O-rings made usually of nitrile, and these gaskets swell in the presence of aromatic. So once you have used the engine with jet fuel, the use of a fuel without aromatics will make the seal to shrink and probably cause a problem, if not an accident. So this is important to take into account, because most of the processes that are at this moment approved for producing the renewable jet fuel they don't produce aromatics, only a couple of them. Well, you can see here that the fancy name that they have chosen for renewable jet fuel or biojet fuel or whatever is Sustainable Aviation Fuel, SAF. This is the name that you can find a lot of information about. There are some differences with gasoline and diesel. Diesel and gasoline are burned, are combusted in an intermittent cylinder. I mean, the cylinder you burn the diesel and gasoline produce intermittent combustion, whereas the jet fuel is burned in a turbine by continuous combustion. For diesel and gasoline, the main thing that you want is that they behave as a fuel. Maybe you need some lubricity properties, but they are not as important. In a turbine, fuel acts as a fuel, but also as a lubricant, and also very important, the heat transfer properties. Jet fuel is used in the turbine to dissipate heat and to move heat from one place to the other. If you think about gasoline and diesel, they can be blended with something which is very different. Gasoline is C4 to C12 or something like that. Ethanol is an alcohol with 2 carbons. Diesel is heavier, is made of hydrocarbons, has no oxygen, but we can blend it with FAME, with fatty acid methyl ester, which is a methyl ester with oxygen, with a very different composition. When you see the regulation of sustainable aviation fuel with the fuel, there's no reference to composition directly in the standard. I mean, if you read it not very carefully, you may think that you can add anything to the jet fuel as renewable jet fuel. Ethanol and FAME must meet compositions, must meet a standard. I did name the biodiesel standard. This is DN 14214, where the composition content of fatty acid methyl ester, the content of diglycerides and triglycerides is set. The amount of water is set. And you can blend it. It does not depend from which material you produce ethanol or which material you produce the biodiesel. The standard does not say anything about this. In the case of this fuel, if you want to use sustainable aviation fuel, you only can do it commercially if it's been approved, and that includes not only the raw material but the production process. The cause of this is because for having a plane accident, usually if you see the last that have happened, they occur by a chain of failures. Something fails and something more fails because of this, and the pilot does not know that has to do something, then you have an accident. Yet jet fuel can be the single cause of an accident, and that is something that the standard tries or gets to avoid. Another different thing with the gasoline and diesel that we can buy almost everywhere. Wherever we go, we can find a petrol station. Jet fuel is used centralized. That means that storage and distribution is different for those two fuels, those three fuels. Well, how do you approve a jet fuel, renewable jet fuel? Well, not only by following this or fulfilling the same properties that the standard says for the fossil jet fuel. I mean, this is implied in one of the steps, but there are more steps. And this is everything about this procedure is due to security reasons. The procedure that a new fuel, sustainable aviation fuel, must follow to be considered commercial is set in this standard, D4054 of the ASTM, and it comprises 4 different steps or tiers. In the first step, the blend of jet fuel and sustainable aviation fuel must fulfill exactly the same standard that the 100% jet fuel, meaning that it doesn't matter the composition, but the properties that has to have. Only the aromatic content, water content refers to composition. But once that you have a fuel that has the same properties, as it is not the standard fossil fuel, must go to a second step. In the second step, more properties need to be measured and compared with the fossil jet fuel, like Campbell number distribution, vapor pressure, lubricity. Electrical properties are also important because of the static charges that can happen when the fuel is moving. And for this, you need to test a nice amount. Here you can see 4 liters for the first tier, 400 liters for the second one. Once you have your sustainable fuel that follows this or fulfills all the necessary properties that you need, you go to test the different parts of the engine. So fuel control, pumps, the start-stop system of the engine, then you need to test. And finally, you test in real the whole engine. 2 days ago, this news appeared in this web page, in different web pages, about a test that the Dutch company KLM had made. Boeing has already made tests. I think the British Airways have already made tests. So probably in the future, in the short future, we'll have more processes approved to be used as renewable fuel. Here you can see that this process is not fast, up to 3 years, as it's not cheap, up to $15 million US. That's something that really constrains the the development of these fuels, now a fast track is allowed, that you don't need to follow these four tiers or steps, and only fulfill some compositional and thermal stability properties. But at that moment, you only can use 10% maximum by volume in the jet fuel if you approve your fuel by this fast track method. Now, at this moment, there are 7 processes approved that follow in these 3 categories: thermochemical route by Fischer-Tropsch, that means gasification of biomass or other material, and Fischer-Tropsch synthesis, from lipid to jet, and from sugar to jet. I will show it very briefly. That's the last part that I'm going to show to you. The Fischer-Tropsch process is the same that we have seen for gasoline or for diesel. There are 2 processes. One of them is the FT-SPK, and the other one is the same /A that produces aromatics. Didn't find exactly the procedure that they produce aromatics, but I think it's not from biomass, but from coal. You can add it seems that you can add the aromatics to the Fischer-Tropsch product. Anyway, you can produce from linear alkanes. You can produce aromatics in the oil refineries. Do this in order to increase the aromatic content of certain streams. These 2 processes are allowed to be introduced in the jet fuel with a maximum of 50% by volume. In the lipid to jet route, there are 2 or 3, I don't remember now, 2 or 3 processes. This one, which is the process that the Finnish company Neste uses, also has been developed a different one by the catalyst company Vegan or by the Italian company Eni. It consists on hydrotreating the lipids to produce different fractions. One of them you separate as call it green jet sustainable aviation fuel. This one was approved last year. It consists in a 2-step process: supercritical hydrothermolysis in the presence of water. I mean, you mix the lipid source with water and carry out the reaction at supercritical conditions. You can see here more in this paper. You can see more details about the reaction conditions. This reaction is really fast. It happens in about a residence time of 2 minutes. After that, you need to do a hydrotreating process to like saturate olefins and do the cracking and aromatization. With this process, the product has a very similar composition to jet fuel, including aromatics. The 3rd process, the lipid to jet, has also been recently approved. In this case, it been proposed by a Japanese company, IHI. You have here, you can see later the web page, and is for the production of jet fuel from the lipid obtained from an algae, the algae that you can see here. This process has been approved by the fast track method of the standard 4054. So the maximum blend allowed is 10%. And there are 2 routes approved for producing sustainable aviation fuel from alcohol. The first one is the SIP, which calls for the synthetic isoparaffin. In this process, cellulose is hydrolyzed enzymatically, and by fermentation with a genetically modified yeast, single or almost a single compound is produced, which is farnesene. This farnesene has several applications, and if you hydrogenate it, you produce farnesan as a single molecule, C15 hydrocarbon, branch hydrocarbon, then can be used as fuel. As there is a product with a single like compound, the standard only allows to mix it with jet fuel for a commercial use up to 10%. And there are two different processes approved in the same annex of the standard that are in the route of alcohol to jet. This one is for the Spanish American company Gevo. The Gevo produces from cornstarch and by fermentation isobutanol, and isobutanol is then hydrogenated to olefins. In this case, the range of carbon numbers that you get in this process is more limited than in others, so the maximum blend is 30% by volume. The LanzaTech process is a mixture between alcohol to jet and thermochemical because they produce syngas by gasification of biomass. The syngas is fermented to produce ethanol. Ethanol is dehydrated to ethylene and then polymerized to olefins. Then the olefins are hydrogenated and in a process of typical refinery process, fractionated to get the jet diesel fraction. Well, that's all on my talk. Just to finish, more than conclusions, I would like to highlight some take-home messages that I think they are significant or important, at least for me. First one is that it's very urgent to change the primary energy sources because we will run out of oil soon. But if you think about the environment, then it is extremely urgent to change the energy sources that we are using. I hope that this change I will see, that it will change with change that is coming, that is going to change the pool of energetic products and processes that we are using for our modern life. European Union foresees that in 10 years they will need to invest 1 trillion euros, not only take into account public money, but also they want to draw a lot of private money for developing processes. I read somewhere that 75% of the energy that we will consume in the future will be produced by processes that at this moment are not commercial. So for all of you that are in this business of research and development of processes, I think there is a big room to do things. And also, although the goal is to produce biofuels, advanced biofuels, we need not to forget that a lot of hydrogen is used in virtually all the processes that are on the development or are already commercial. All the processes use hydrogen. So the production of renewable hydrogen is also important, and we need also to work on the development of catalysts. And well, that's all on my side. I hope you didn't find this talk very boring. If you want to make any question, I will try to solve it, or probably will show my ignorance. Or if you want to comment anything, we can discuss about it.
Muchas gracias, José Luis.
Thierry.
Fue muy interesante y divertido. Do we have questions for Professor Sanchez? Alors, dites votre nom.
My question is there anything alive? Anyone alive there?
Or some of them have to write a resume, so they're definitely going to have questions. Yeah, Mike, go on.
Hi, can you hear me?
Yeah.
Good. I have a question on the European Green Deal. I'm not very familiar with it, so maybe you can answer this. So, is the European Green Deal a true effort towards reducing European emissions, or is it just the continent kind of shifting their emissions to China and the third world and just calling it done? Thanks.
I think that part of both. I mean, as an engineer, or scientist, you think is zero emission is zero emission. I mean, you don't use coal, you don't use natural gas, you don't use oil. Zero emissions. If you, I didn't read in detail the Green Deal, but if you have a look more or less, you start to see that, for example, advanced biofuels count double. You use an advanced biofuel, the CO2 that you don't emit, you count double. When you see that CO2 taxation and CO2 rights selling and buying, I think it's like greenwashing of the environmental policies. But on the other side, this is the most serious effort that I've seen in order to actually decrease the CO2 emissions. I don't know if I've answered your question, or maybe I didn't understand it very well, Mike.
No, I think that's good. Thanks.
Okay.
Other questions? I have one. We have studied in the class the energy mix from Quebec, for instance, and what are the renewable energies that are actually in the Spanish mix?
Well, in Spain we have mainly solar and aeolic energy. But when you come here, you'll see that from Barcelona to Zaragoza, or from Madrid to Zaragoza, or wherever place you go, you see the windmills for producing electricity. And there are some also, not that much because it's more expensive, less developed. There can also be solar gardens. I don't know how you call it here. Is solar garden. We produce solar. There is a plant to produce electricity not far from here. It's 10 electrical megawatts, which produces energy from straw, burning straw. And there have been some gasification trials that I don't think they've been very successful. So for us, it's mainly wind and solar power. It is true that diesel is 7% by volume biodiesel. Ethanol in the gasoline, the E5 that we consume, not really sure where does it come from, or even it is bio or not. But we are using it. Biodiesel, for example, we import from cheap countries as Argentina, for example, makes dumping and plants that we have, they are closed. There are still a few, but the biodiesel ban make a lot of plants here that most of them are closed.
Okay, thank you. Do we have questions? So if not, I would like to thank you a lot for this presentation, and nos vemos pronto.
Okay. If you have my email, if you have any comment of something that you didn't like or it could be improved, I will really appreciate that.
That was perfect.
Okay.
Thank you.
Thank you very much. I don't know who's there. I don't know if Max is there to say hello, or is a shy guy.
Are you asleep?
Hello.
Hey, you're alive.
Hello, Jose Luis. How are you doing?
How are you?
I'm great. What about you?
Well, you can see me. I cannot see you, but you can see me more or less the same. I cannot. I have no complaints.
Oh, there you go. Hi, how are you? Actually, I have a question.
Okay.
So how is your lignin doing with your biodiesel oxidation stability?
Well, very well, thank you. Biodiesel, for all of you that you don't know, has double bonds and it's organic, so it's prone to oxidation. In order to be commercialized, you need to extend the like the life. Lignin or phenolics are antioxidants, natural antioxidants. We are producing them from lignin. We have increased by, I think, I'm not really sure. Zainab is one of our students is there. Zainab, I don't know if she has the record or she broke. Maybe she broke my record of 600% or of increase over the need biodiesel. Yeah, I know. I know you're here, Zainab, but I don't remember if you broke my record. With Zainab is working with argan lignin, and the lignin from argan is really good. I mean, it blends better with biodiesel.
So it's actually soluble now, right?
Not all. It's more soluble than the lignin from straw, but not all. I have some ideas in order to try to determine to measure what are the soluble parts, but still didn't have time. And at this moment, you are ruining my siesta time. So I think later I will go for it. Yeah.
All right. Thank you.
So we don't have any questions. So we'd like to thank you, Jose Luis, for the presentation on behalf of everybody. And for the student of my class, you have until 11:30 to submit your resume. So thank you, everybody.